All right, we're going to start today. Yeah?
There just is a course that stopped at 2:30.
Oh, okay. All right, but I'm still going to start. All right, so we have some announcements to make. The first one is that we have a room for the lab, and it's in a museum. That's the only room that was available. There's a map of how to get there. It's on the web page, on our class web page. All right, the second announcement, oh my God, what was that? Sorry. All right, the second announcement is that we are going to approve everybody that is registering, but I'm not getting any emails. And it's not just you. If you're having this problem, I haven't gotten one email. There's several of you that have tried this and have not been approved, and that's the problem. So we're trying to figure out why that's happening. And once we do, then everybody should be fine. But like I said, as far as we're concerned, we want to approve everybody. And the second thing is that if you're not a Harvard student and you should email Verena so you can get a Piazza account. And once you have that, then you can follow the discussion on cross registration that we're going to have. Once we figure it out, we'll announce it there. Okay? All right. All right, so the second announcement is about the digital literacy project. If they're looking for volunteers, and what they do is they teach computer science and other technological advances in high schools, middle schools in the Boston area. Tom Silver over there is one of the people working in the project. You can ask him questions if you want to participate. Okay. So let's get started. So today we're going to have a lecture on some concepts related to exploratory data analysis. And in the second part, we're going to talk a little bit about data wrangling, just the basics so you can get started. So you can start importing data into Python and doing some of the stuff we do here. It's going to be pretty basic, but we'll spend the last half hour doing that. So a lot of what we do when we analyze data starts with data exploration, just looking at the data and trying to see what the general properties are, if there's any problems with the data that need to be fixed before we start something more formal. And we're going to learn some graphs, some graphing techniques that are actually you probably have seen and maybe already know about. We're going to go over them again and show you how these can be useful for understanding your data and also making discoveries with your data. There are cases where all you do is data exploration. You figure something out just from looking at the data and you present a picture and you're done. That's your analysis. That is something that happens often, and sometimes these pictures are very, very convincing. I'll give you a couple of examples, and you don't really even have to do any analysis to make it formal or rigorous. The picture is really worth more than 1,000 statistics in this case. So here's a quote from Tukey. There's an important quote, I think. So Tukey is just a personal story. He's the advisor of my advisor. So I guess he's my grandfather. And he has a very nice quote I like. He says, the greatest value of a picture, he's talking about exploratory data analysis, is when it forces us to notice what we never expected to see. So there are cases where I think data visualization is overdone and people just make really pretty things, but they don't really force us to notice anything. They just look pretty. So that's something to keep in mind when you make a picture. In the context of data analysis, you want the picture to convey a message that is not obvious from just looking at the numbers or simple summaries. All right, so that's we're going to talk a little bit about that today. And I want to motivate the whole thing with the graphics editor at the New York Times. I'm going to show you some really nice data exploration infographics that have appeared in the New York Times, and they're either done or led by Amanda Cox, who has an MS in statistics. You can call her a data scientist, and now she's in charge of all the pretty things you see in the New York Times. That's one of the types of jobs that are available to people who have the knowledge that we're going to learn in this class. Although for some of the stuff they do, you have to know a little bit more like interactive graphics, but that's something you can pick up. So I'm going to show you one example, if this lets me go there, of one of the figures she's made. So this is a very simple picture, but very informative about unemployment rates in the US. So if you can, I don't know if you can see the x-axis is time, starting when around the crisis, January 2007, and ending in September 2002. So you can see there's a flat line, and then all of a sudden around the financial crisis, it starts going up. Very simple picture. But what's really neat about this picture is that it stratifies into groups, so you can see that there are some groups of people that are doing much worse than the average. And if you just float around with your mouse, you can see Hispanic men and women age 45 and older. And you just go down here and you can see Asian, etc. So you have it all stratified. So that's a very powerful data visualization. So again, just by making a picture and looking at that, you can see clear differences between different groups. One of the things that comes out of that picture very quickly is that a college degree makes you be way down at the bottom, the unemployment graph. And it didn't actually go up too much. All right, and if you do it by people who took this class, it's 0. All right. So I'm going to show you a couple of examples of pictures that they're not even that pretty, but they really show you something interesting just by making a picture. So the first example relates to an exam, scores from an exam that is given in New York. It's called the Regents exam, which you have to get a 65 to pass. So these data are collected for many reasons. People study them and make sure that certain areas aren't doing worse than others, and there's no schools that are really doing poorly. So the data is available. You can get it and make pictures. So here's a picture that was posted in the New York Times. And all this is it's called the histogram. And we're going to learn about the histograms today. All it does is it gives you for every score how many students got that score. Pretty much. Very simple, right? So I'm going to let you look at that picture. And as Tukey says, it's going to force you to notice something that's problematic. So look at it, look for just a little bit, and realize the problem. You see it? See what's going on? Can you tell what the score, the limit score is just from the picture? Oh, I'm supposed to use the mouse. So if you come here, you see that there's nobody got a 64. Maybe 2 people got a 64 in all New York. I don't know how much that is. It's probably more. But look at how many people got a 65. It's not what you expect. From experience, we have seen that exam score data has this bell shape, and it certainly doesn't have a dip right ahead of some arbitrary number and then goes up. So again, simple picture shows something important. Okay, everybody noticed what I was talking about? We'll move on to the next one. So here's another neat one. This is, again, it is a histogram. You go, I'm showing you the whole page, the whole New York Times, because this was in the front cover. And I'm going to just go to the actual figure. It's right here. Make it a little bigger if I can. All right, so look here. So this is Clinton versus Obama in 2008. I don't know if you guys remember that. But it was a very close race in the primary, Democratic primary. And what this graph is showing you is how the difference between Obama and Clinton by state, and it piles it up as a histogram. So again, it's a very simple picture, but it kind of tells you some information, and there's a couple of interesting things that show up that catch our attention. So this is a little bit of a special histogram because it has the states. The little boxes actually has the state names. In a typical histogram, you just show the heights. You don't actually put little names like that, but it's still a histogram. So you can click around and see different voting patterns. There's women, they voted for Hillary more. There's blacks, they voted for Obama more. Whites, etc. And there's one that I find interesting, it's college grads. Or is it postgraduates? See a little, can you tell where Hillary's from? So you can see Arkansas way out there as an outlier. All right, so those are two examples of how simple little pictures can be very informative. Imagine instead of these pictures, you had in front of you the tables. It wouldn't, it'd be hard to see that. You probably would see, oh look, it's minus 50, but not as easy as with visuals. All right, so here's another one that is also based on the idea of a histogram. It's very pretty. Sometimes when the New York Times, they really make them pretty as well as informative. So what is this one? This is one of the things that we might be able to do towards the end of the class, especially if you learn some of the interactive software packages that on your own, because I'm not sure we're going to get there in the class. So what is this showing? This is trying to answer the question of how much tax companies pay in the U.S. Right, so there's all this debate, like claiming that in the U.S. companies don't pay taxes and they get all these subsidies. So this is the data. And it's kind of like a histogram because they're stacking up these like what look like pebbles or rocks to show height, or in this case just width, to tell you how many companies are in certain ranges. So the x-axis is the tax rate paid, and then you can see where the majority of the companies are in here. Right, so most companies pay about 30%, and very few pay more than 60%, very few pay nothing. And this one's interactive again. You can see what the company is. There's Pfizer. And the size of the circle is the size of the company in, I think, earnings. So you can go visit this and just play around with it, see what companies pay a lot and which ones pay nothing. All right. Nope, get away. All right, so now, the heights that you guys entered the other night, we're going to just very quickly go through this so you can see the types of things you can do with data summaries and visualizations. And it's not very interesting, this one, but it's something that is related to us, so maybe that will make it slightly more interesting. So these are the heights that were entered by you guys in the last class, and what we want to do is summarize these numbers, summarize the heights of this class to, say, somebody who's outside and wants to know how tall we are as a class. So how can we do that? How do we do that? Here is, by the way, if you want to look at the data yourself, it's on the internet. You can click on that, and something you're going to learn in our class is how do you just import that in one line of code into Python. So you can then look through it and do what I've done here. So here are the first six people who entered their heights. Some people entered it before the class started. I'm pretty impressed. 140, someone already entered their height. So how would you go about describing this to somebody who's not here to see us? Any ideas? What would be a description? I mean, one thing we can do is go to this website and look at all the heights. And they would have 200 plus numbers there to look at. That's not very useful. So what else could we do? That's the question. Anybody want to yell out a possibility? Comes to mind? Yeah, go ahead. Histogram, perfect. That's a nice one. For this particular data, there's something even better, but we'll get to that. But the histogram is good enough. We actually can do it with 4 numbers for this data set. With 4 numbers, we can pretty much describe the whole class. I'm going to explain how. All right, so now before we get there, and here's something you don't learn. So up to now, what you're going to see today is very much like a statistics class. But something that they don't teach you in statistics classes is that it's never easy to get this. Even something as simple as give me your height in inches turns out to be a difficult problem. So here are a couple of entries that weren't in inches. So if I ask the computer to plot 5 little line, 4 2 little lines, it's not going to know what to do. Right? That's not a number. And I like the spirit of this person. No way that person, she is going to use the English system. All right. So this is actually pretty easy to fix. But think about this now. There's no statistical procedure for this. There's really no computer algorithm for this. This is kind of a new thing, and that's one of the things we learn in this class is to deal with reality. This is reality. So you'll see the code. We'll put the code up, and you'll learn to do it yourself. How to deal with it. So there are ways to do this to sort of write a little algorithm that says if you see a feet sign and an inch sign, then take the first number, grab the first number, multiply it by 12, and then add the second one. Right? You can just write that little piece of code. If you see a cm, divide by 2.54. That's all simple computer program. So I did that, and I thought I was done, but then I found that I wasn't, because there's a very, very small people here that are 6 inches tall. And I like this guy. He came in at 11:55, went into his computer and said, I'm going to screw him with a... And there's also another one up there, it's 9,000. So you can tell what some of these, I don't know what these guys are thinking, but they're probably having fun. But you can see what some of the others are. You can imagine what they are. And again, this is not statistics, this is not computer science. What is this? That's what I call data science. It's just thinking about all these things. 6. Someone says, how tall are you in inches? And they said, I'm 6 feet tall. Right? And then this person said, I'm 5'11". Right? You see it? I don't know. Here's another one. I don't know what this is. But the other ones, I'm 5'0" meters. Yeah, that's a pretty tall woman, but maybe. Yeah, you can see what's going on, right? So this person's probably 5, 2.5, etc. So how do we deal with these? I take them out. And I have the script I have for doing this is I say anything that is, and we're going to learn about this, certain distance away from the average is out. How do I decide that distance? That's one of the things we're going to learn here. Okay, so that's data wrangling. We're going to learn about that throughout the course. We're going to be doing this it's rare to find a data set where you don't have to do some of this sort of looking and figuring out. And by the way, how did I know that this happened? Well, one thing that happens is when you say, turn these into numbers, it says I can't. But the way I find these is because I make a plot, I make a histogram, and I see that there's these numbers that are way out in places where there shouldn't be numbers. So I can't see these right away because remember there's 200 and plus numbers to look through. But as soon as I make the histogram, I can see them immediately. All right, so that's another powerful thing about data exploration. All right, so here's one concept I want you to learn and think about. Statisticians call this the cumulative distribution function. You don't have to worry about that, but I might, because I'm trained as a statistician, say CDF every once in a while, and this is what I mean. I'll try not to say it. All right, so it's a very simple concept, and what we're doing is we're simplifying the list of numbers in the most raw form so that we don't lose any information at all. So what I'm saying, instead of when somebody tells me what are the heights of your class, instead of saying 6, 6, 6, 1, 6, 2, 6, 6, 6, right? I don't want to repeat 6 over and over again. Instead I say there's so many people that are less than 5'2", so many people that are less than 5'3", etc. And that describes the list of numbers just the same, right? Because I know exactly how much of each one there is. So that function is the first way we can summarize without losing any information. And I can make a little picture of it. Right? So for every A, I just use A as an arbitrary number, I compute the proportion of people who are shorter than that number. So there's 2 lines there. Anybody want to guess what those 2 lines are? Men and women, right? Males and females. So which one's males? The blue, or purple. It's purple and orange. It's not blue and pink. So, and for those that are colorblind, it's dashed and red. And solid. So what I can do here is I can say how many people are taller than what is 5'10"? About 50%. How many men are taller than 75 inches? No, practically none, etc. Right? So you can get you can answer any question like that. Now this picture, this is a very nice concept to have in your heads, but we rarely use it for data exploration. Instead, we make the histogram, which the histogram tells you instead of how many people are shorter than this or that, you take intervals and report how many people are in those intervals. So we have that, about 12% of men are about 5'10", etc. So you have for every inch, in this particular histogram, for every inch, we see the proportion of people. So if you like calculus, you can think of the other picture as the integral of this function. But it doesn't matter. I don't know how helpful that is. Yeah?
Sorry, I need to unplug the now.
You do?
Yeah. The extension school students can't hear the microphones. We hope that the laptop microphone is going to be.
So I should just talk here then. Right? You're going to...
Yeah, maybe you can get it from over there.
Oh, I can stand here. All right. So that's the histogram. All right, now, the reason I say we can do this with just 4 numbers is because these data, if you look at the histogram and you have enough experience, you can pretty quickly look at that and know that that's very close to following what in science we call the bell curve, the normal distribution, the Gaussian distribution. These are all the same thing. So it comes up in nature a lot, and there's a mathematical explanation for that. But it just comes up with heights, weights, score tests. There's many instances where it comes up, and this is one of them. So this is the formula for the histogram. If you want to make a histogram without recording any data except the mean and the standard deviation, which I'm going to explain in a second, you can do it without actually looking at the list at all. So notice what I'm doing there. I'm saying the proportion between A and B, any A and B, doesn't matter what A and B, there's a formula for it. I don't have to collect data. Well, I do for 2 things. There's 2 things there we don't know. We know what pi is. That's just a number. We know y is the thing that we want to, y is the data. And then there's 2 things we don't know, that little mu symbol and the sigma. Mu stands for m, mean or average, and sigma stands for s, standard deviation. So those 2 numbers, if I know those 2 numbers, I can figure out any proportion in any interval. So that's it. I have 2 numbers, and I'm done. I summarize the entire data set with 2 numbers. So this is what that curve looks like, the theoretical curve. It's centered at that average. And then it has 68% of the data within 1 standard deviation, 95 within 2, and about 99.9 5 or something high within 3. And that's what the normal distribution is. So if we know if we take that list of numbers and I report the mean, for men it was 70, 510, and the standard deviation is 3. It's easy to compute in Python, very, very easy. For females it was 65 inches, and that's 5'5", and 3 standard deviations as well. So now, instead of, so for any person, if you want to know how many people are of a certain height or taller or shorter, all you have to do is compute what is called the standard units of that quantity. So you subtract the average, you divide by the standard deviation, and basically what you're doing is you're saying, I'm turning into a number that answers the question, how many standard deviations away is this data point from the average? That's what this Z is. That's it. So, just to give you a very clear example, in this class, 6'4" male is 2 standard deviations away. So their Z, their standard unit, there is 2. So now I can immediately, without actually counting, without actually asking people to stand up, I know that I can tell you how many people there are that are taller than a 6'4" male. And in this case, it's going to be less than 5%. It's going to be about 2%, 2.5%. So we can ask the people to stand. I'm not going to do that, but I can tell you I'm right because I actually computed it already. Right, so here are heights, the real proportion that are shorter than that height, and the approximation that the normal distribution gives us. So all I'm saying here is, if the data is normally distributed, as it is very often, then there's a very, very nice summary we can use, and it's to report the mean and the standard deviation, and that's why you see it so often in newspapers. Sometimes it's, the average person has this value and with a standard deviation of this. That's because they're basically telling you how everybody behaves, what the data is for everybody with just those 2 numbers. So that's the ultimate summary that we can use in exploratory data analysis. If the data is normal, it's going to be a great short summary, just 2 numbers that does everything. And we need 2 here because there's the males and the females are normally distributed. If we put them all together, they're not quite normally distributed. So one other plot that I'm going to, this is all like boring stuff from statistics, but we're going to see why it's useful later. One plot that you want to make is when data is normally distributed, there's a lot of things you can do. There's a lot of machinery you can use that makes things easier. So if you want to make that assumption about your data, you want to make sure it's true, the best plot for doing that is called a quantile-quantile plot, a QQ plot. So what we do is we compute for each percentile, 1%, 2%, 3%. We say, in our class, what was the number that was associated with 1%, for which 1% of people were shorter than that? What was the number for which 2% was? 3%. We do it for every percent. So we get 2 numbers, one from our class and one from the normal approximation. That is a formula. You can get it from Python with you remember that formula I showed you? You can just say, you just write this, you write this, oh, you can't see that. That's how I get it. You just type it in there and you get your answer. How many people are 2 standard deviations, are shorter than 2 standard deviations away from the mean? 97%, just like that. When I was your age and there were no computers, there was books and you would look at the back. You've never seen these things? And you would have a table that said, for 1 it's this much, for 1.1 it's this much, for 1.11 it's this much. But now you just have to type it on a computer. Maybe I'll bring one of those books so you can see how hard life was. All right. Okay, so that's the QQ plot. Okay, any questions up to now? Very simple stuff. No? Okay. All right, two variables. So I'm going to give you the same idea of summarizing two variables. So for summarizing two variables, there's certain circumstances where all we need are 5 numbers. Just 5 numbers summarizes the whole thing. So this is a famous example from when all these ideas started to get attention, and it had to do with genetics and heredity, which they would notice that your father's height and son's height had a relationship. Taller dads had taller sons. So this is a picture of that data. You can see there's a relationship that kind of goes up. So if I want to summarize this data, how do I do that? One thing I can do is just show you a scatter plot. That's what this is called, and we're going to see a lot of scatter plots in this class. Perhaps the most common picture we're going to make is going to be some version of a scatter plot. If you plot something against time, it's a scatter plot in a way. You have time on one axis and points on the other. But the name is usually reserved when you have two variables that are measurements. So this is father height, son's height. Okay, so let's say I ask you to predict if I asked you to predict the height of a randomly selected son, what would you say? I tell you, behind that door, there's one of those people, one of those sons. How tall is he? Go ahead. Oh, well, good answer, but what if I say I'm not going to tell you? Then what do you answer? Take the middle. You already saw the picture. It's a curve, and the highest point is in the middle. So you take the average. The average height is going to be your best guess. That's where the biggest value is. All right, but now I'm going to change it. And I'm going to say, what if I tell you the father is 72 inches tall? Now what's your answer? So you take the middle, you take all the people, 71, you take all the parents who are 71, and you make a histogram of those. It looks like a bell curve too. But the middle, instead of being at 68, where this is you guys are taller than these people because they're from the 19th century. They didn't have as much food. So 68 is the average person, but the sons of 71-inch tall men are taller as expected, but they're not the mean. Actually, the mean's out here somewhere. The mean is not at 71. So I'm not going to say, oh, if the father's 71, then the son is 71. If I do that, I'm going to overestimate. So if I go and do this, we're going to get back to this when we start doing machine learning and prediction. But if I do that for every strata, 60, 61, 62, and I compute the mean at each point, I'm going to get something that's almost on a straight line. That's what that blue line is. Anybody know what that line is called? Hint, it's down there. It's the regression line. How many have heard of regression? Good. So it's called regression because of this picture, because the statistician that first looked at this said, hey, the sons regress to the mean. They go down towards the mean. So it's not that line is not an identity line. It's slightly lower. And the slope of that line, so if I'm going to predict, if I tell you that is 3 inches taller than the average, that's 1 standard deviation away. That's what the x is, right? So x minus the average dad divided by the standard deviation of that is 1. That father is 1 standard deviation too tall. What should I predict for the son? Well, that formula, that line, tells me it's going to be something slightly lower. That row there, that little P-looking thing is called row, is not going to be 1. It's going to be slightly lower. And that thing is called the correlation. So the correlation between the father's sons and the dad's son is called the correlation. In this case, it's 0.5. I calculate that from the data. So that gives me the formula. I can make that prediction. And the other thing I can do now is this means that I can predict, I can summarize this entire data set with the mean of each group, the standard deviations of a group, and the correlation. Now this works, I didn't say this until now, this works only for certain data sets, and it's when the data is jointly normal. So you'll see like football shapes, American football, not the other one. So if they have some kind of football shape, then all these ideas apply. So that's why you sometimes see data summarized as mean, standard deviation, and the correlation. Okay, so that's all great. We actually use that. Sometimes I use it all the time when I know the data is normal. I just can keep those two numbers in my head, and I know everything I need to know about the data. But it's not always a good idea to summarize data with just those four or five numbers. This is a famous case, famous counterexample to doing this. It's not real data, it's fake, but it's the most famous textbook example. So these four data sets, there's pairs of numbers, right? So it's like the father and son thing. They all have the same mean. X and Y have the same mean, same standard deviation, and the same correlation. So the summaries, if I were going to summarize these four data sets using this naive approach, you would think they're all the same. Look how different they are. Point being, that those summaries don't work here because those aren't football shaped. The first one is, you see it? Can you see a football there? See, I'm like the Greeks that could see all kinds of stuff in the stars. So you can kind of see it, but not this. That's not a football, that's not a football, and that's not a football. Right? So it works over there, but in these cases, it doesn't, and that's why these numbers are not good summaries, and why we encourage you, and we're going to teach you a lot about ways to look at data, summarize data in different ways, many times graphically. And the next several lectures are going to be all on techniques for doing this efficiently, properly, and also beautifully as well. It is nice to see something that looks beautiful. So one real example. That's a fake example, but here's one that's very commonly used. So this is, again, back to the one number case. This is a compensation for 199 US CEOs in the year 2000. And there's a histogram. Okay, so if I summarize that data with the mean and the standard deviation, what would I be telling you? What do you get from that information? If I say, oh, the average CEO makes $600,000, that's so much. Well, you guys probably don't think that's too much. But that's not really useful, because when you hear this summary of mean and standard deviation, what you should be thinking is, oh, there's a bell shape, and there's a average and a standard deviation. Here, there's none of that. In fact, it's really, really off. 84% of CEOs make less than 600,000. Right? They're all way out there at the very end. So in cases like this, that's a mistake you see often in newspapers and even in scientific publications. There's this idea that you always have to summarize the data set with a mean and standard deviation. That's only useful when the data is approximately normal. Okay? So this just serves as a simple motivation for the idea of making pictures, looking at data, and finding appropriate ways to tell stories that give you information that's important. Okay? So any questions? All simple. Okay. So what we're going to do for the rest of the class, are you going to use your computer?
Just for a very brief announcement at 3.
And then you're going to switch? Okay. So what we're going to do as I said at the beginning, now we're going to start getting into the nitty-gritty of Python code so that you can read in data and start doing some of this for yourself. And like I said, next week we're going to start looking at more complicated data where we're looking at the right summaries and the right stratification really reveals interesting aspects of the data. Okay, you want this? All right. I'll stand here so you can give me the.
Could you just go to the course page? Oops. Works? Yes? No? Too loud? Okay. So just because I need to switch the laptops and I need to make sure the Blackboard Collaborate is working for the extension school students, if you haven't done so already, on our homepage, there's this lecture slides. And if you open that, it's going to take you to our Google Drive. And please download this Lecture 2 read table. That's an IPython notebook. Basically, you just download all the files in there. All you're getting extra is the lecture from last time. So I guess, so please download those files. And while you do that, if you haven't done so already, I'm going to switch the laptops. OK, let's go from here. So there actually are two ways to get the slides from the lecture. The Google Drive is the more cumbersome and complicated one for the IPython notebooks. But it's the one I think everybody here should be familiar with. So you can literally just click there, right, and it takes you to the Google Drive. Those of you who already know Git, we do have a repository on GitHub. So if you know how to use Git, you can just go to the CS109 repository, and that has one for 2014. This one is public, and you just clone that repository with the URL that is down here. If you do not know how to do this, just come to the lab tomorrow, and I'm going to explain it. Because this, in the end, is going to be more convenient for you, and it gives you a nice entry point to GitHub because you're only downloading files. You're not submitting anything. So it's a gentle way to start using Git. OK, I hope most of you have already started with the homeworks, which means you most probably have installed Anaconda. How many of you have a working IPython notebook set up? Cool. OK. Because we're going to use IPython notebooks now. So this is my command prompt from Anaconda. And what you can do is you can just really start IPython itself, and you get this Python command shell. And this is different from the regular Python shell. And the two aspects that I use the most that make IPython really nice for me are there's a tab completion. So if I define a string, some text, blah, blah, blah. Then if I go some text dot, you can just hit tab normally. Oh, great. What? Oh. Oh, this works as well, so I should have done this. And it gives you all the different commands that you can use on a string. Like I know that there are a lot of people here who haven't used Python, but you all should have some basic programming experience, so this can help a lot. If you know that this now is a string, right, then you know string dot tab completion is going to list all the different functions that are there. And then, for example, I can see there's a find command here, right? Find. Find sounds interesting. The second really helpful thing about IPython is this. I can type a question mark after my function, hit enter, and it's going to give me the documentation of that function. And this can get you pretty far, also with respect to the homeworks. And this also works from within the IPython notebook. So we are not going to use this prompt normally, also not in the homeworks. So I'm going to exit this. And instead now, you can see that I have this lecture here, and it has this ending IPy notebook. So I am now, instead of only writing IPython, I type IPython notebook, and I give it the name of the notebook I want to see. And if I hit enter now, it opens automatically the browser for me. And here you can see it opened the notebook for where this lecture is in. And I told you to download all those files. My lecture slides are always going to have the cell in the beginning just to adjust the fonts and everything. So this should make your IPython notebook very large, font size-wise. This is so you can see everything. If you don't want this to happen, you can just uncomment that line and hit Shift-Enter while being in that cell. And it's going to execute. And now you see it just changed the complete layout from the talk mode to something that might be better for you on your laptops now. So if you want to follow along with the lecture, you can just use those slides now, have the same IPython notebook as I do, and by just uncommenting that line, you have something that might be better for you to read. Okay, and this I'm just going to execute because it makes all the necessary imports. Skipping that. So this is what I just showed you. This is how IPython basically evolved over time. Like they started with just this interactive Python interpreter, and then you had something where you could show graphics inline, and by now you have this whole interactive mode that even just runs in your browser. And I think it's pretty neat, because these slides now are interactive. You're going to see I can change the code that is written there, and you can directly see the output. So we can discuss code also in class and like play around with it. And this guy, Damian Avila, so I really want to give him kudos and thank you, because he's the guy who made this possible. He programmed the whole framework that allows us to have those interactive slides. And here you can see I can just do this, and it updates. And to execute the cell, you need to be in there, and then you hit Shift-Enter. OK, everybody so far on board with me? Nobody's saying anything. Yes, OK. Who can follow along now, like on their laptops? Give me a hand signal. OK, that's only about half. This is going to be fine for this class. If you really have trouble with the setup, please come to the lab tomorrow, and we're going to make sure that you're able to follow along in class, because I think this is going to be more fun. So as Raphael said, we're going to go briefly over how do we read in a data file and do a basic visualization of it, so that you can start playing around when Mark is going to teach you some cool visualizations next week. So how to load a table. There's a really, really cool Python library called Pandas. And I don't know why, but nobody shows cute Pandas pictures with it. So Pandas is a whole library for basically doing everything that you need as a data scientist. I think you can really say that. So it can do a lot more than we're going to cover here. I'm only going to go over the very basics. And then we're going to have a follow-up lecture where I'm going to teach you how to scrape data from the web. So not just read a file, but actually scrape data from the web, and then do cool stuff with it using all this other functionality that Pandas offers you. So, and this is really all there is to reading a file from the web. I specify the URL here. So this is now a file I actually uploaded to our repository, but there are other data sets out there that are already conveniently formatted for you, and it's a comma, it's a CSV file, or in this case, it's just a TXT file with a table in it. So all I need to do is tell it where to find it, and then PD, I imported the Pandas library to always have the PD in the beginning. So whenever you see PD in the code, this is a function I use from that library. You can import it in a way that you don't have to type PD always. I do this explicitly because I want you to know where to find that function when you want to use it later. So we use this Pandas function that is called read table. And we just give it that URL. And that's it. You're there. And what I do here now is So I store this table in a variable called ranking, and I only take the first 30 rows of it. And then this gives me an output of that actual data here. So ranking.head, ranking itself now is a data frame. And head is a function from a data frame that always gives you only the first 5 rows. And this is very useful if you just want to know briefly what is in there. So then you can use ranking.head. And you see here, this is a university ranking. So you have the actual rank here, and you have the name of the school. And this ranking is totally outdated, and I subject to the first place, but it is what it is. And you can see the different variables here that they use to rank the universities. And if we go further to the right, why can't I do that? I'm not sure why this is not working. Okay, they have other stuff there like life sciences and engineering and all of that. So this is how they rank the universities. And we now have all this data from the text file in our ranking variable. That's really all there is to getting basic data from the web. So now we have our data in a pandas frame, and now we want to plot it somehow. So there is the library in Python to do plots, and it's called matplotlib. And for such simple examples, it's really cool. You can also look at the web page. Oh, see, I already Googled stuff here. If you look at the web page, these are cool visualizations that you can do with matplotlib. And I think there's really a lot you can do with this. You can have 3D plots and everything you want, but that comes with an overhead that you need to learn. And pandas, we're going to see, offers you some functions to make your life easier instead. So we have our ranking. And you could see that the ranking had this overall score. So what I'm doing is I'm accessing the overall column of the ranking and say, this is the data I want to plot. And then matplotlib has this bar plot here. So I just give it the rows here. This is my x-axis, right? This is the index, 0, 1, 2, 3. And then I have the data I actually want to plot. And all I have to do is call the show function, and I get this plot down here. So it's as easy, 3 lines, selecting one column, right? Calling that bar plot function, making that window show up, and you have your bar plot. So it goes even easier. It gets even easier. Plotting with pandas, you can just directly use the data to plot. That is the data frame object, and just call the plot function. And this plot function works with a lot of things. So if I just leave this away, this kind bar, oops, I get an error. Oh, okay. Sorry for this. I need to run all the cells once. Oh, it doesn't know the variables. So if you follow along, you actually need to execute the cells because those variables otherwise are not known. There we go. So if I use just the plot function, it does the normal line plot, right, of this. And if I say kind, the kind of plot I want to have is actually a bar plot, then it updates this and I immediately have my bar plot. This is really the simplest way I found to quickly inspect your data. So how do they rank the universities? We have this whole table now, and it turns out actually not all of those columns are really important for the ranking. They mainly just use this academic peer review. You can see it has a weight of 40%. And then they also use the faculty-student ratio, citations per faculty, recruiter review, and the international orientation. If you want to see more about this data set, You can look it up in this link, but this is the part that is important for us at the moment. So these are the relevant columns then from our data. We have the academic, the faculty, this is the faculty-student ratio, the citations they got, how good of an employer they are, and the international. So what I'm doing here is, you remember our ranking had all these different columns, right? So now I'm specifying a list of strings with the names of the columns that are important. These are the ones that actually are counting for the ranking. Let me actually show you. Let me do this. So this is the ranking we had, right? We have all these different columns up there. And now if I do ranking dot overall, we had this before. It's just going to choose that one column with the overall score. You can also do it this way. Ranking at overall. So instead now I wrote the actual name of the column. And this is what I'm doing here. I'm specifying a list of all the columns that I want with all the names. And this is how this works. So you have the ranking here, and you have the list here with all the relevant columns, and it automatically, for you, selects the different sub-columns. And then we can save those in a new variable called ranking categories. And this is all there is to it. So the bottom line is, you first, as in every programming language, have to learn these basics, how they work, but then you can be very fast with just a few lines. I mean, try to do that in C or C++. It's going to take you a lot more lines of code. And now it turned out those categories were weighted, right? So we need to multiply those values by the different weights they were assigned. And all I have to do now is I specify a list of the weights. And even though this is the different size, right? My ranking categories is this whole large table with all the different values in it. And my weights here are just one large list. And still, I can just multiply those, and it automatically does the right thing. It multiplies each column by the value that is in this list. So now we have everything weighted, and we can do this bar plot again, but let's do multiple bar plots. So now I want actually to see each category, and this is what is here. So you have a large bar at the beginning, because this had this, I think there was academic performance. This has this 0.4 weight, right? So it's natural that this bar is much higher than the rest. And here's our first thing that I wanted you to do. You saw that this legend, maybe you actually didn't see that. So if you look at this plot, it looks fairly okay, but this legend up here, not really readable and a bit screwed up. So what you can do is, who has programmed MATLAB before, maybe is familiar with this. This returns a variable that is a handle to that figure. So this is what we did before, right? I just have my ranking categories. I take the first 5 rows just to make it the plot larger. And then I have my plot here. And this plot here, you can basically think of as stored in this axis handle. And what I want to do now is I want to move the legend to a different place. So I say here legend false, which means don't give it to me right away. And then instead, we want to put the legend where we want it. So I call this axis here. This has a function, .legend. And this I can give a location and this bounding box to anchor. So I want you to play around with this and make this legend come to the right side. Try it. Like you can go and put different values here. 0.2. You can see the legend moved a bit to the right. What do I need to type to get my legend to the right? Who gets the number first gets to shout. Give me coordinates. 1 on the right. First one is 1. Yes. Can we make that a bit higher, that it's nicely in the middle? What? Where 1.5? 0.5, here. Yes. Nice. So you can see this is basically the coordinate system for this legend, and you can move it around in any way you want. But you need to know a bit what you're doing, because this pandas frame, plotting, all, underlying is matplotlib. Like this plt.show function comes from matplotlib. So the two go together. Pandas basically gives you a very nice interface to that matplotlib library. So you can forget about all the ugly stuff that is behind there with all the X's and everything. But then you can also really tweak those figures. So when we go into storytelling afterwards with like visualizations that look really, really nice and cool, when you don't just want to explore your data, matplotlib is going to give you all this range of freedom if you want it. If not, you can also have already basic visualizations with just 3 lines. So you can also just get this stacked, and all you need to do is really add this stack command here. So I just say stack true, and everything gets stacked on top of each other for the different categories. And now that we have those nicely on top of each other, we can also make them lay down and get them horizontal, and this enables us to show a lot more than just 5. And finally, this is actually something that might be not readable for the extension school students later on, but you can follow along on the notebook. You can put the names of the universities to the left here. I don't know why this is so gray. So what I did is I got the school names. Remember, that was on the very left were the school names listed. And you can actually set an index of this pandas frame. And then it doesn't count those rows anymore, 0, 1, 2, 3. It actually knows now. MIT, Harvard, I forgot who's third. I have to remember the important parts. So, oh, I actually can look it up, right? MIT, Harvard, University of Cambridge was third. So now I actually have the names of all the universities, and I have the stacked ranking to the right. And all of this with such 4 lines. 4 lines. If I would have done the index before, it's really just this 1 line. So this was just supposed to be a short primer to show that you can get visualizations fairly fast, very easy. We're already through this. So by now you should know how to read a data file, right? Remember, you just have to specify that URL. Next line, load all of this into pandas data frame. Then you can just call the plot function of that data frame. And you also know now how to get help, like really use that tab completion and use that question mark. It works also in the IPython notebook. And matplotlib is great. You can do really cool visualizations, but to get to the really cool ones, you need to know a bit what you're doing. But for exploratory data analysis, you can go very far with pandas. Questions for this? Yes?
What happens if we try to plot from the terminal?
Plot what?
What happens if we try to plot a graph from the terminal?
From the terminal. He wants to know if you can plot a graph from the terminal.
Oh, the question is how we can plot inside the IPython terminal?
No, the terminal window, not the notebook.
Like,
There.
okay, you can use the exact same commands in that IPython terminal. What's it going to do is it's going to open a window showing you your plot. Yeah. And then there is this intermediate thing. You can also load a Qt interface, I think, for the IPython terminal itself. And then it can also do this inline. Then it looks more like the IPython notebook. But normally, if you just go to the plain terminal, you do the plot, it will open a new window with the figure. Yeah?
So for this class, what's
Sorry? The most. So you, yeah, but was this meant for the project, for the homeworks, or during the lectures? Okay, the question was how static the data is. This lecture now is not gonna call for scraping, but when we had the scraping lecture, you will also be able to scrape real data from the web. So I can basically tell you, go to Wikipedia, look at all the countries there, give me the number of people living there. Or give me, I don't know, we're gonna see an example how to scrape happy hours from the LA downtown site, according to preferences. So once you know and get the hang of data scraping, it's really easy to also keep updated with data files. For now, just because we haven't done scraping yet, it's gonna be convenient in a file for you. So I have to say, in total, that was a bit more boring than I thought. Like following along. I'm doing this for the first time with the IPython notebooks. I think we need to switch this a bit more up. How many of you were able to follow along with what I was doing? How many of those actually thought this was fun? Oh, okay. I'm gonna think about a different mode for this because I don't want you to fall asleep in the lecture like going code. This is still stuff you have to learn. I think it can be exciting, but I'm gonna try and do this in a different way, I think. Then that's all for today. Again, that GitHub part is still gonna be useful. So please, if you haven't used GitHub before, come to the lab tomorrow, 10 to 12.